In this video, we introduce the Heisenberg Uncertainty Principle. Alright, so we're trying to understand the behavior of very small particles that have quantum behavior. And the idea is that when you go to very small particles moving in a very small region of space, you actually have a blurred line between what is a wave and what is a particle, such that particles like electrons are going to have some sort of wave properties. For example, we know that electrons can diffract much as electromagnetic radiation does. Right, so here's one of the problems that we face when we have that wave-particle duality. If I were to ask about a wave, which looks like this, for example, and I would say this is the function of a wave and this is a function of the distance, and I would say, well, in what region of space is this wave exactly? And well, what we would say is that, well, the wave is here, but it's also here, and it's here, and it's there, and it's here, and it's there, and it's there. Okay, with different amplitudes, or different function values, but the wave is kind of everywhere, right? Well, if the wave gets to zero right here, we'll say, well, right at this point, we actually don't have any wave. But elsewhere, it looks like we actually have wave everywhere. Now, the problem is that we actually have to transform this into what a particle is doing. Okay, so suppose that we have a particle right here, okay? And this particle is macroscopic. Okay, so this particle is macroscopic, which means that it's moving from the left to the right. We can ask, well, suppose that the particle is moving and we freeze it in time, and the particle is right here. And we will say, well, where is this particle at this particular moment in time? And you will say, right here, at this value of x. And again, this works very well for a macroscopic object like a baseball. You can predict the trajectory of a baseball quite well. But again, when you look at a very small particle, right, so this is now a very small region of space, okay, so we're talking about angstroms to nanometers, and the mass is very small, like that of electron, and what happens is that you don't have that anymore. Instead, you have wave properties, right? So we have already talked about the fact that the way that we understand where the particle is using the value of the wave function squared, okay, which might be something like this. Okay, so when we ask another question, where is the particle? We can't say exactly the particle is here or there or there. We can say, well, the particle has some probability of being in between these two regions of space. It has a different probability of being right here, and it has a different probability of being right here. Notice that we can never say where the particle is very precisely. Okay, and again, that's part of this wave-particle duality that happens when you go to very small masses in very small regions of space. Okay, so this inability to predict exactly where the particle is, and instead having to talk in terms of probability, that is all well codified by what we call the Heisenberg Uncertainty Principle. Okay, and we can write here the Heisenberg Uncertainty Principle simply by doing the following. The statement is this, and the way to read this is the uncertainty in determining the position of a particle multiplied by the uncertainty in determining the linear momentum of a particle has to be at least this value, h over 4 pi. Okay, let's unfold that momentum, which is simply mass times uncertainty and velocity. Notice that the mass of particles is well determined, right? We know exactly what the mass of an electron is. We know exactly what the mass of a particle is. Okay? The error is going to be in the velocity. This is going to be equal to h over 4 pi, okay, which is the same thing as saying that the error in determining the position multiplied by the error in determining the velocity has to be larger than this value. Okay, so it's very straightforward to see that these errors are going to be very small when we actually talk about macroscopic particles. For example, if we talk about, say, a baseball, which has a mass of about 145 grams, or to make it a little bit easier, let's assume that this number is 0.1 kilograms. Okay? And we say, well, let's assume that we want to have a very low error in determining what the speed of the baseball is. Okay, so the error is going to be a millionth of a mile per hour. Okay, more or less, a millionth of mile per hour, which means that you can tell the speed of this baseball with 6 decimal points. That's essentially what this is. right? Let's make this number be 10 to the minus 6 meters per second, or miles per hour, which are very close to each other. Okay, then if you actually think about the value of this h, is 6.626 10 to the minus 34 joules per second, and you crunch the numbers, what you're going to find is that this minus 6 goes to with minus 34, that transforms into minus 28, and then here you have about 0.1 multiplied by 10, that kind of cancels each other out. So you're going to have something on the order of 10 to the minus 28 meters. Okay, 10 to the minus 28 meters, right? So this delta x for this baseball, of which we want to determine the velocity very precisely, that error is going to be 10 to the minus 28 meters approximately, right? But this particle, this baseball, is moving in a region of space that is of meters range, right? So, for example, if this baseball is being thrown from the mound to the batter's box, that distance is about 10 meters or so, right? So you have an error of 10 to the minus 28 meters in a distance covered that is about 10 meters. This error is completely insignificant, okay? And what this means is that even if we want a very, very precise value of velocity, there's essentially no restriction in how accurately we could determine the position of that particle if this particle is macroscopic, right? So the key is that that particle has to have a large mass. Now, things are entirely different when we think about microscopic particles, okay, like electrons. If you now plug in there the mass of an electron, okay, 9.1, 10 to the minus 31 kilograms, all right, and you sort of use the same numbers, now you're going to have something like of the order of 10 to the minus 37 in the denominator, maybe 36 with this 10. Okay, so again, you have an error now, which is going to be about 30 orders of magnitude greater than this, which means that the error in determining the position of the electron is going to be about 100 meters. And here's the problem. Electrons don't move in very long ranges. When you think about the electron motion in a molecule, that electron motion is going to be confined in an angstrom, maybe a nanometer. Okay, so the total distance covered by the electron now is about 10 to the minus 9 typically, okay, on the scale of this, okay, plus or minus 1 order of magnitude, okay, meters. But the error is 100 meters. Essentially what this means is that if you want to determine the velocity of the electron with a lot of precision, then you will have essentially no idea what the electron is in this range. Okay, and that is actually a consequence of this wave-particle duality, the fact that these electrons are described by waves, and again, we cannot tell exactly where they are, we can only talk about in terms of probability. Okay? And again, all of that is codified in this expression. Essentially, for a quantum particle, if you determine the position very accurately, then you will have no idea what the momentum or the velocity is. Or if you want to determine the velocity very accurately, then you will have no idea of where the position of the particle is. Okay, so that in a nutshell is what the Heisenberg Uncertainty Principle is.